My name is Adel Gastli. I'm going to present to you this chapter, which is about gate drive circuits. The lectures are divided into 3 parts. This is the first part. The contents of this chapter are as follows. An introduction, MOSFET IGBT gate drives, BGT base drives, isolation of gate and base drives, thyristor firing circuits, thyristor converters, gating circuits, and then we'll finish with summaries. Let's start with the introduction and ask ourselves this question. Why do we need special gate drive circuits? Actually, there are a few answers for that. And let's first start by giving some general ones, and we'll explain them further in the next section of this chapter. The first reason for having gate drive circuits is related to the switching frequency. For fast switching on and off of controlled power semiconductor switches, there is a need to use special gating circuits which can control the commutations of the switches, making them turn on and turn off very fast, and thus minimizing the switching losses. These circuits are called gate drive circuits, and they are designed specifically for each type of power semiconductor switch so that they make it turn on and off very fast, as I said before, hence reducing the switching losses. So in this chapter, we are going to see some examples of how you can design such circuits for few types of power semiconductor switches. A second answer to this question is related to high and low level switch combinations, which we are going to explain a bit through this following example. This figure shows a typical bridge converter which has 4 transistors. As you can see here, there are 2 transistors connected on the high level side and 2 others connected at the low level side. In a circuit like this one, where we have high and low levels transistors, it is not possible to connect the output of the logic gate signal generators directly to the gate of the transistors. So in this case, we need to isolate the gate drive circuit from the power circuit in order to achieve a floating voltage between the gates and the source, which is not using a common ground as the logic gate signal generators and the power converters. A third answer to the same question of why do we need a gate drive circuit is related to circuit protections. In fact, in many high power applications, and for the sake of protection, it is advisable to isolate the low power control circuits, microcontroller side for example, from the high power circuits, which are the power converter and the load. So these are just brief and general answers to this question, which help us understand better the objective of the content of this chapter. We will see more in details and more examples on the gate drive circuits for the main types of power semiconductor switches in the next few sections. Now let's study the MOSFET gate drive circuit. Before talking about the gate drive circuit for the MOSFET, let's first recall the mode of operation and characteristic of a MOSFET through this short video.
A metal oxide semiconductor field effect transistor, MOSFET, is made of P or N-type doped silicon. In this example, the substrate is composed of P-type doped silicon. On this substrate, there are electrons, shown here in white, as well as holes, known as electron holes, shown here in green. Through ion implantation, 2 N-type regions are formed. The term N-type signifies the fact that adjacent to the normal silicon electrons, there are additional electrons which are free to move around, shown here in red. An insulating layer is needed. This is typically produced with silicon dioxide. Above this, a layer of aluminum is applied via vapor deposition. Finally, a second layer composed of silicon dioxide is applied, in which contact holes are created through etching. The transistor is now ready. Taken together, there is a P-type substrate with 2 strongly N-type regions. as well as electrical contacts which provide the transistor with the necessary current and voltage potential, known as the source, gate, drain and bulk terminals. Source and bulk are often connected to each other, so they share the same source of current. The objective is to control the flow of current between source and drain. This is accomplished with the gate. If there is no voltage potential at the gate, there will be no current because no carriers of current are available between the two N-type regions, shown here in red. However, should there be a positive voltage potential on the gate, a positive electrical field builds up, which attracts electrons in the p-type layer and repels holes. These electrons form an N-channel that can carry electrons from source to drain. It should be noted that the current between source and drain can be increased through raising the voltage potential, which leads to a stronger electrical field and thereby a larger N-channel. Since no current is able to flow between source and drain when there is no potential on the gate, this type of transistor is called enhancement mode MOSFET. MOSFETs are increasingly used in integrated circuits, for example those used for microprocessors. Since only electrons or only electron holes alone take part in carrying current, this type of transistor is considered to be a type of unipolar transistor.
What is important to retain from this animation is that the faster you establish an electric field between the gate and the source, the faster the switch will turn on. And the faster you cancel this electric field, the faster you stop the current flow from the drain to the source and the transistor turns off. As it was presented in the previous animation, an N-channel MOSFET is constructed as shown here. As you may know, different semiconductor materials develop virtual or parasitic capacitance between them. Therefore, we can represent the MOSFET electric equivalent circuit as follows. Therefore, if we want to establish an electric field between the gate and the source, we have to charge the capacitor CGS. And if we want to cancel this field, we have to charge this capacitor also. So allowing faster charge and discharge of this capacitor CGS makes the switching speed of the MOSFET higher. And this is the ultimate goal and function of most of the transistor gate circuits. So the turning on time of a MOSFET depends on the charging time of its input or gate capacitance. Having a circuit like this one will allow fast charging of the gate capacitor. However, the charging time and the steady-state gate current cannot be controlled and limited. Therefore, we need to introduce some other elements in the circuit to be able to control these parameters. Introducing an RC circuit like this one will allow to reduce the turn-on time by fast charging the capacitor and at the same time limiting the steady-state gate current through the resistance R1. Let's see more in details how this circuit works. When the gate voltage is set high, the gate current follows the path shown in red color here. The initial charging current of the capacitance is given by this equation, which shows that the initial peak charging current is limited by just the source resistance Rs. To increase this peak current, we need to increase the source voltage level. The steady-state value of the voltage across the gate resistance, which is the gate voltage, is usually determined by this equation. Notice that this voltage depends on the gate source voltage, the source resistance, the resistance R1, which is limiting the gate current, the resistance RG, which is the gate resistance, And typical values are taken between 10 to 20 volts for turning on and keeping the transistor in its on state. Note that the above equation considers that the steady state gate source current is negligible, which is actually the case when the gate source capacitor is fully charged. In order to achieve the switching speeds of the order of 100 nanosecond or less, the gate drive circuit should have a low output impedance and should be able to sink and source relatively large currents. The MOSFET will act as a source during its turn-off transition, where large gate current is discharged from the gate capacitance into the gate circuit. This is shown in this figure as a negative spike. And it will act as a sink during its turning on transition when it requires large currents to charge its gate capacitance very fast. This is shown as a positive spike in this figure. The totem-pole arrangement shown in this figure is capable of sourcing and sinking large currents. The PNP and NPN transistors act as emitter followers and offer a low impedance to the circuit. These two transistors are very fast. They operate in the linear region rather than in the saturation mode. Thereby, they minimize the delay time. Let's see how such a circuit works. When Vin is high, the output of the comparator inverter is low, which triggers the PNP transistor that will turn off the MOSFET and the drain source voltage becomes high. So the PNP transistor presents a very low impedance during the sourcing of the MOSFET. Now if Vin is low, the output of the comparator inverter is high, which triggers the upper NPN transistor that will turn on the MOSFET and the drain source voltage becomes low while a current flows into the drain and source path of the MOSFET. The NPN transistor presents a very low impedance during the current sinking phase of the MOSFET gate current. The key points to retain from these sections are: MOSFET or IGBT is a voltage controlled device. Applying a gate voltage turns it on and it draws negligible gate current at steady state. The gate drive circuit should have low impedance for fast turn on. The gate drive circuit should have sourcing and sinking capabilities. And finally, MOSFET and IGBT have very similar gate drive circuits. This is because an IGBT has actually a MOSFET in its gate side. This is the end of this part. Please join us in the next part, and thank you for listening.